I cannot express how excited I am to talk to this crowd. This organization is really near and dear to my heart. Some of you, first of all, I must apologize for the change from the title, but this is a talk that I've given pre-pandemic to the Math Society. And since I only had a couple of days to prepare, I decided to give this talk. But really, what I said math in that lecture could also be interpreted as the quantum mechanics of nanotechnology, because one is the same as the other, as you will see. So why nanotechnology? Because this is come to be my field. By training, I am a solid-state physicist. By the way, you may have heard of this. You may have heard this talk in its entirety. So I am sorry if this is the second time around for some of you. As I said, I didn't have time to prepare a new one. I only had a few days. So I'm just using an old. But hopefully this sparks some nice discussions. Why nanotechnology? As I said, my field is computational solid-state physics. But a very prominent application of solid-state physics nowadays is nanoscale systems. Why do we concentrate so much on this nano part? Well, it's a bit of a buzzword, first of all. I mean, it sounds cool. Nano means really, really tiny. But that's not so much the point. Don't focus so much on the nano part of nanotechnology. After all, it's been around for 20 years. It's cool, but not super cool anymore, even, because it's sort of, you know, everybody has gotten used to this idea of tiny little things finite. However, the nice part, the interesting part of this field is that things are really, really small. And what interests me particularly, and what I'll emphasize today several times, is the idea of confinement. So what is fascinating about systems that are very small, not microscopic only, but really, really small, really, really tiny systems, is the idea of confinement. So, for us physicists, of course, everything begins with the Schrodinger equation. Now, if you know what it is, if you've studied quantum physics or quantum mechanics, great. If you don't know what it is, if you've never seen it before, it's okay. So, it is essentially, and this talk is going to be somewhat math heavy, but it's okay. The ideas are what matter. So, we assume that given a system, any system, the amount of information that can be extracted from that system is encoded entirely in this equation. So in this equation here, I have an h, and then I have this funny little caret, hat on top of h, and then I have this function, psi, and then on the other side of this equation, I have some constant, e, and then the function back. If you know what this means, you already know. But for those of you, maybe coming from prep school or first year, this means the following. This h thing is what we call an operator, and it is essentially some constants. This is Planck's constant. This is the mass of your particle, okay, or your object, let's say, times the second derivative. Why? Because this is how quantum mechanics is. The second derivative, this is just the derivative, plus some potential term. So there are two elements in this equation. The first term here is the operator form of kinetic energy. Okay? We call this an operator because by itself, it doesn't mean anything. It has to operate on something. In fact, when it operates onto a function, and when you put it through some more manipulations, you are going to get the kinetic energy of your system. Okay, this part is the same in all systems, and what distinguishes one system from the other is this potential term. And for us, this is going to be what is important. Now, this particular operator is called the Hamiltonian. It is composed of the kinetic energy part. This is not a number, it is a derivative. So by itself, it doesn't mean anything. Okay? And V is the potential. Now here I am using just one variable, R, which means that I have one single particle in my system. All right. how about this psi? Again, if you know, you know, but if you don't know, in quantum mechanics, very different from classical interpretation, the solution of this equation, so you can solve this equation, given the system, you can find out what psi is, given this energy term, okay, and this is energy. It corresponds to the probability amplitude of the appearance of an electron at some point r. Probability amplitude. All right. Now, as I said, we can solve. My objective is to solve this equation for example, a very tiny system in a nanoscale system. That's my objective as a solid-state physicist or a person that's working in the field of nanoscale objects. My objective is to solve this Schrodinger equation for my particular system. But let's start with something much simpler. Let's talk about a free particle. A free particle means that the potential term is zero. So it means that if you have a particle, it is not affected by any electric field, magnetic field, any walls, any confinement, okay? It is literally free. Now, if you solve, the mathematical details are not important for those of you who haven't seen it, but if you solve the Schrodinger equation for a free particle, taking the potential to be zero, you are going to get this term here. This is essentially e to the ikr. This is essentially just a sine or a cosine, let's say. So a free particle has a wave function that oscillates like a sine or a cosine. All right? Now, how about this 1 over square root of v in front? It is there because while psi itself, the probability amplitude, does not carry a lot of physical meaning, psi squared means the probability, or is related to the probability of finding a particle at point r. So the connection between classical physics and quantum physics arises from the interpretation of psi squared as the probability of finding the particle at r. And this is very important. This is the crux of quantum mechanics. Unfortunately, I realized that I made a mistake here, so please, oh no, it's okay actually, it's okay. Is it okay? Yeah, this shouldn't be here, sorry. Please erase this from your minds. This 1 over v shouldn't be here. Now, since I am interpreting psi squared as the probability, so your electron can be here, 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 okay? If you add all the probabilities of existing anywhere, it should integrate to, or it should add up to 1. So your particle is somewhere, okay? However, this function here is not normalizable, meaning that you cannot take the integral. The integral is undefined. So what we do is we say, okay, I am not going to worry about my electron being anywhere in the universe. I'm just going to assume that it exists within some volume. Let's say this room. Okay? So I confine my electron, my free electron, to this room. All right. Now, do you have any questions up to this point?
What does V?
What is V?
What does V mean in the first question?
Okay, V here is just the volume that you are considering. If you are talking about free particles, you cannot really talk about the particle existing anywhere in the universe. You must think about it as existing in some finite volume. Let's say this room. Considering an electron existing in this room and the universe are not that different. Because I know that electrons, for example, of this object, let's say, are in this room, more or less. So I don't have to consider the extension of the electrons around here to the rest of the universe. I am okay with just considering this room. So you must always have a volume when you think about free particles. Very large, really, really large, but finite. Good. Other questions? Go ahead.
How do we
decide on the volume?
You don't. It's just arbitrary. Since it's arbitrary, so you may take 7 square cubic meters. I can take 100 cubic meters. The results we obtain should be the same since it's arbitrary. So you will see that in nanotube problems, it will just cancel out. Okay? So one of those tricks to agree, like make physics agree with math, kind of, to make sure that we can work coherently within the confines of math. Alright, so far I've just talked about one particle. Of course, in this case, and I am concentrating on electrons, because usually nuclei in this context, for solid state problems or for nanotechnology problems, the nuclei of atoms are so massive, so much more heavy, so much heavier than electrons, that I am taking my electrons to be the quantum mechanical particle, not so much the nuclei. So I am worried about the electrons, because nuclei are really large, and therefore most of the time we treat them classically. Okay, so here I am also neglecting the interaction of electrons. For nanotechnology, for a lot of the nanotechnology problems, this approximation turns out to be okay, right? In some of them, it really fails very badly. But today, we are not going to talk about this problem. So each electron behaves as if it were on its own, not interacting with the other electrons. Okay. And then the effect of the other electrons you can indirectly include through this V. So, single particle. Alright, so why am I telling you all of that? Next I'm going to introduce the idea of taking a free electron and confining it. So just a shapeless, featureless electron, just by being confined in certain directions, you will see that the physics of my problem changes drastically. So if I have, for instance, a big chunk of silicon, which is a semiconductor that is used in all of technology, right? If I have a big chunk of silicon, the behavior of the silicon is going to be widely different than if I make a tiny little wire out of silicon, for example. That is going to be the main idea. And the easiest way to demonstrate this idea is just to take a free electron and confine it to a very small space. And you will see how the physics changes. So, let's start by a three-dimensional object, like I said, a chunk of silicon or piece of metal, big piece of metal, or big chunk of glass. So let's start with a macroscopic three-dimensional material, and let's cut it until we cannot cut it anymore. Let's cut it down to 1 atom thick. So in the 2 dimensions, let's say in these 2 dimensions, in this plane, let's have its extension go to large values, so large in these 2 dimensions, and in the 3rd dimension, tiny, atomically thick. Now, such materials exist already. One very famous example is graphene. So graphene, okay, did I say what it's made out of? No, so I'll ask you. Which element is graphene made out of? Carbon. In fact, when you are writing with your mechanical pencil or your regular pencil, you see that it leaves a trace, a black trace, okay? That is several layers of graphene being stripped off from your pencil, actually. So you can see it in everyday life, basically. This material is a fantastic material. It is now regularly produced, even in Turkey. There are companies that make this material. And it has a very particular structure. It's atomically thin, and carbon atoms like to form this hexagonal shape, and it is really flat. So this is just a model. This isn't an actual graphene because you can't really see atoms this clearly. This is actual graphene. As you can see, it is perfect, just like promised here. And what is this used for? If you make like a larger material out of this graphene, called, for instance, graphene foam, you can use it in insulation because it's very light. It is quite sturdy. And also, it's a good insulator of heat. So, in some phones, for example, I read somewhere that some phones, cell phones, were using this as a thermal sink already. Next, let's take our two-dimensional object and confine it in one more dimension. So for instance, let's take my graphene, a tiny strip of my graphene, and let's roll it into a cylinder. So imagine graphene being rolled into a tiny cylinder with radius a few nanometers. So really tiny, much smaller than human hair, because you can see human hair, but you cannot see these things by the naked eye. So imagine really long, maybe millimeter long, at this scale that is very long, maybe centimeter long, but nanometer thick, okay? 1,000,000 times smaller than its long. So this object can be seen as a one-dimensional object. Of course, nothing is one-dimensional really. Usually we call these objects quasi-one-dimensional, but for all intents and purposes, your electrons are confined in one dimension. These things are made just like graphene. You can also structure these one-dimensional tubes, which are called nanotubes. When you say nanotube, you usually mean carbon nanotube, but you can make nanotubes out of many materials. Also, you can fill in, you can imagine like a tiny little wire, not empty like this, not perfectly cylindrical, very small, very tiny, but filled maybe. These we call nanowires. So this is a forest of copper nanowires. You can use it for many things. Usually this kind of stuff is used either as sensors, this kind of forest upright nano wires are used as sensors, or maybe in this case for electronic purposes, because it's copper. So I went from 3 dimensions, I took my electrons, I confined them, so I made their universe, I collapsed their universe into 2 dimensions. I made something like graphene, for instance. Then I confined them even further to 1 dimension, so I made their universe 1-dimensional. I'll do one more. I will collapse them all the way down to 0 dimension. Of course, once again, nothing is really mathematically 0-dimensional, because then that would be a point, and an atom has more extension than an actual point. But for our purposes, we can regard these systems as 0-dimensional. So this is the balled up version of graphene. It has the geometry, I think, identically of a soccer ball, right? Pentagons and hexagons, and it's made out of carbon. So this thing exists. Okay? Or you can, from metals, you can make these quantum dots. These are called quantum dots for reasons that will become clear. So you can make really tiny, a few hundred atom clusters. And by changing their shape and size, you can do different things. Now, there is one important application that will make sense when we cover the next few slides. Here are solutions of quantum dots of different sizes. So it goes from, I don't know, 1 nanometer, 2 nanometers, 3 nanometers, 0.5 nanometers, okay? So in these different vials, in each vial, there is a solution, suspended, colloidal suspension, let's say, I don't know, suspended number of quantum dots with different radii. So this is one radius, this is another radius, this is another radius. And as you can see, when you shine light on them, they reflect back, all of them different light. Just by changing the size of the metal nanoparticle. Does anyone have an idea why this is? Maybe you're already working in this field, or maybe you heard of this. Does anyone know why this happens?
Are they used in Samsung displays? Like
No idea. I feel like they would be expensive, but maybe.
They are expensive.
Yeah, I mean, everything is expensive now, but I don't know if there's an actual application of this, but this is an actual experiment. You can do this. Does anyone know why the size of a metal particle would affect its interaction with light? Any idea? Even if you don't know, you can guess.
Wavelength.
Okay. That needs to go in a full sentence. Wavelength of what? Why? How?
My
Who?
English isn't that good for explanation.
Sorry?
Maybe some wavelengths are reflecting or absorbed by that
Sure.
quantum dots.
Absolutely. So different wavelengths are getting absorbed and reflected with different probabilities for different radii, but why? Listen. So this is the full idea behind confinement. So let's go back to math. Go ahead.
Is it that the states of the electrons change?
Yes. So by changing the size, your friend is suggesting that correctly, that when you change the size of these materials, let's go back. Okay. When you change the size of these materials, you actually change the available quantum mechanical energy levels that your electrons can exist in. Now we are going to look at why this happens, but this is just a function of confinement. Now, if you take macroscopic amount of a metal, let's say you take a macroscopic amount of copper, you double it, you triple it, you make it larger, its properties usually doesn't change. Unless, of course, you are not looking at properties that are really about the surface. So if you are looking at the bulk properties of the material, size shouldn't really matter for macroscopic systems. But for microscopic systems, nanoscale systems, they are so tiny that you can basically, if they are small enough, change the properties of your material by just rearranging atoms. So they are very sensitive to changes at that really small nanoscale. So let's explore this idea a little bit further. So how does one describe confinement? Consider a free particle in this room. Okay. Now let me make the ceiling of this room come really close to the floor. So you're really confining your electron to a few nanometers, whereas the rest of the room remains the same. What happens to your electron now? Is it free or is it not free? Not free? Or is it something in between? So it's not as free as it were in the three-dimensional case, but it's still free in these two dimensions. It can move wherever it wants, okay, in this two-dimensional space. But in the third dimension, it can only move in a very tiny little length. Okay, so what happens when you make particles be surrounded by really thick walls? Now, of course, in classical physics, if you and I are kicking around a ball in this room, if we close the windows, the ball has to remain in this room. In quantum mechanics, it's not quite like that. The particles can also move beyond the walls, but if your walls are long enough, quantum mechanical confinement is also possible. But how does that reflect on the wave function? So remember that the wave function of my free particle was just a sine and cosine with any wavelength it wants. There was nothing to restrict the wavelength. It could have any wavelength it wanted. Now, if I put really strong walls, since my particle cannot exist beyond these walls, the probability has to go to 0. Which means that at the ends of the two walls, so here are my walls, right? At either wall, my function has to go to 0. This means that I can only fit 1/2 wavelength, 2/2 wavelengths, 3/2 wavelengths, so on and so forth. So the liberty of the electron to have any wavelength it wants has been taken away. So confinement has brought about discretization, which means that you can only have just these wavelengths, either 2L, L, what did I do? Okay. This one, I don't know, 3/2, 2L. So those are the only wavelengths you can have. Alright, so what? So, in this one dimension where the electron is confined, my solutions have, again, still a sinusoidal form, but with particular wavelengths. Alright? So this K here is basically the inverse of your wavelength times 2 pi. This is called the wave number. So instead of using the wavelength, we often use the wave number. So your wave number here, which is the inverse of the wavelength, has been discretized. Your wavelength, your wave number, can only be an integer multiple of 2 pi divided by the length of your confinement. Is this somewhat clear? So for those of you who studied quantum physics, this is the famous particle in a box problem, even modern physics. So if you don't know what I'm talking about, just remember, if an electron is free, it can have whatever wavelength it wants. If it is confined, it cannot have whatever wavelength it wants. The wavelength is discretized, and there are many wavelengths that are now forgeable. Okay. So these are my energies, these are the values of the energy. Now, let's go back to your friend's idea. The question I asked was, if you confine something and if you change its size, you see that its behavior changes. Maybe it starts to reflect different wavelengths of light, all right? The reason is here. This is a very simple rendition of that. Of course, the real problem is much more complicated. But here is the simple rendition of that. The energy values that just go like h bar squared, Planck's constant squared, times wave number squared divided by 2m. You don't have to understand why this comes from. It just is the energy. Okay? Its energy goes like this. Now look at the energy levels. First of all, they go like an integer. So this is an integer. Okay? An integer squared. Let's put it to one side. Then look at this dependence. So as I make my system smaller and smaller, the energy levels that are available to your electron, okay, the energy levels that are available to your electron are going to get farther and farther apart. Okay? So as you change the size of your system, you effectively change the size or the difference between energy levels. Why is this important from an optical point of view? So why does this cause me to see different colors? Any ideas?
Energy states are different.
Okay, but what has it got to do with optical properties?
Energy levels get smaller and
The electron needs to absorb more energy to jump to the higher state.
Exactly. So, visible light, what you see as a color, depends upon what is absorbed and what is reflected. So if I'm absorbing red light, you see the color, I mean not me, let's say if my shirt is absorbing blue light, you see more of a red color, right? So whether you absorb blue light or not depends upon the distance between your energy levels. Because electron can be here at this energy and then at this energy, right? And when an electromagnetic wave, visible light, in the visible spectrum comes and hits this electron, if it has just the perfect amount of energy, it will jump from this level to this level. Otherwise, this wavelength is not going to be absorbed. Okay? So just by adjusting the distance between energy levels, you can change what wavelength is absorbed and consequently what wavelength is reflected. So by just changing the size, you are able to change the color of your particle. Now, of course, most particles are adjusted such that you cannot see them. I mean, they don't reflect visible light necessarily. But there are many other uses, of course, beyond just this pretty picture. All right. So what did we learn? By means of changing the length, I can change the distance between energy levels. I can change the optical properties. Already, this has, you can go and ask Rashid Hoca, this already has many applications in solar cells, for example. But let's go further. Now look at the energy differences here. So what I'm plotting here is my wave vector, inverse wavelength, okay, and energy as a function of inverse wavelength. Now look at the energy differences. So as the wavelength increases, you get energies that get progressively farther and farther apart for a particle in a box. Now, if you change the wavelength, so for, if you change the size, so if you have a small confinement, let's say, if your size of your confined space is small, there's going to be big jumps between energy levels. if you go, for instance, if your wall is 1 nanometer, you can see the different energy levels by eye at this scale. This is EV. If you change it to 1 micron is still very, very tiny, but as you can see, the energy has now become continuous. So it's almost like I lost the quantum mechanical property of the system. Even at 1 micron, my energy levels are continuous. Okay, so what I mean to say here is that the number of energy levels changes very fast by changing the size. Okay, so what? Now, a lot of optical properties or a lot of spectral properties, spectroscopic properties of materials are given by this equation. You may not have seen it. This is called Fermi's golden rule. It is a transition probability of an electron going from one state to another. And it depends on the number of states in a given interval. So the larger the number of states at a given energy, the larger usually the transition probability. So the main idea here is that the distance between energy levels matter because the number of energy levels in a given interval determines some important properties. Where this equation comes from, don't worry about it. You need to learn perturbation theory in order to derive it, but it doesn't matter. Right. So we said that density of states is just a measure of how many states there are, so how close together your states are. And many important properties depend on it. Now, this density of states mathematically is given by this number of states differentiated by energy. So how fast your number of states change as a function of energy. Okay. For a free particle, if you work this out, it doesn't matter how you get there, but your density of states in 3 dimensions for a free particle, just no confinement, goes like energy to the 1/2. Just remember this energy to the 1/2. All of this junk, you don't need to remember. So, density of states in fully 3-dimensional, non-confined free particle goes like e to the 1/2. So, square root of e. In 2 dimensions, so if your electron is perfectly confined, so that there is no wall, it is really living in a strictly mathematically 2-dimensional universe, it goes like a constant. And in 1 dimension, a strictly 1-dimensional system, your density of states goes like 1 over square root of e. So, 3 dimensions, square root of e, 2 dimensions, constant, 1 dimension, 1 over square root of e. What if it's something in the middle? What if I have 2-dimensional freedom, so my electron can go everywhere in 2 dimensions, but it's confined to, let's say, a couple of nanometers. So it's not a strictly 2-dimensional universe, a couple of nanometers in this dimension. So remember, density of states is very important to know, especially for optical properties. I know what it looks like in 3 dimensions, strictly 3 dimensions. I know what it looks like in strictly 2-dimensional systems. But this in-between, this quasi-2-dimensional universe, what do you think the density of states would look like? This would be the signature of my nanoscale system. So I call a system nanoscale if its density of states behaves in this particular way. So what would it be between 2 and 3 dimensions, this quasi-2-dimensional space? Any guesses? Okay, so let's imagine an electron in this kind of a really funny box where 2 dimensions are large, the 3rd dimension is small. So your energy must have 2 components. In the 3 dimensions, you have free electrons. So that part of your energy really goes like, it can have any wavelength it wants in that direction. It really goes like a continuous number, h bar square, k square. In the 3rd dimension, it is discrete. Okay? So if you look at what kind of a shape, so for different ends, imagine drawing this in 3 dimensions for different ends, what kind of a function would this look like? So if I were to draw this function as a function of kx and ky for different values of nz, what kind of a function is this? What does it look like? So for n equals to 0, let's say, and z equals to 0, what kind of a function is this? It would be a circle if this was equal to a constant. I'm not looking at a constant, I'm not looking for isosurfaces, I'm just looking for this function. So if you have some constant times x squared, what kind of a function is that? It's a parabola. No. Exponential would be e to the something. So if it is x squared, something squared, it's a parabola. If it is x squared plus y squared, or kx squared plus ky squared, it is going to be a parabolic bowl like this. Right? Then if you add a number, if nz is 1, it is the same parabola, just shifted. If nz is 2, it is the same parabola, just shifted. So your energy levels became these sort of kind of like bowls sitting on top of one another, parabola after parabola after parabola. Now, if you calculate so it looks like this, as you can see. If you calculate the density of states for this, you are going to see that, you can do the same thing also for one dimension, but you are going to see that its density of states start to look like this. To me, this was fascinating the first time I learned it. Here you see the signature of three-dimensionality, so your density of states go like square root of E, but it also has signatures of two-dimensional systems where your density of states were a constant. So it goes constant, 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 jump. Constant, 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 jump. And if you look at the overall shape, you will see that it fits very nicely under a hyperbola. So square root of e to the, so square root of e. So as you can see, nanoparticles are neither three-dimensional, or at least confined in two dimensions. They are neither three-dimensional nor two-dimensional. So they are not one or the other. They are completely new, emergent, different systems. You can do the same for confinement to one dimension. Okay, I won't go into the details. So you can make a really tiny wire, very long, but very tiny, tiny wire, and you can confine it in just one dimension. You see that its density of states, or its signature in optical problems, for example, becomes like this. So you have these little blips, and then it goes kind of like this. So in each of these blips, you have actually 1 over square root of e, so that signifies one-dimensionality. But then there's also these sort of blip structure, like these peaks, really sharp peaks, that make it not quite so one-dimensional. So this is the idea of confinement. In 1 or 2 dimensions, everything is normal, it's free. In the confined direction, everything is discretized. So this is why changing the size of your particles at this level changes your physics completely. All right. Now, I'll switch to more realistic examples, but are there any questions up to here? So far, we only talked about just electrons. I didn't even associate this to materials. Any questions up to here?
One of the slides, instead of rolling the surface, why wouldn't it just cut from this side? It would have been made it to a bit thicker.
Instead of rolling it into a circle, what is the, instead of rolling into a circle, what should...
For example, this is the surface, why not just take the edge? Like,
I'm sorry, I lost my glasses, so I really cannot see you, so I can't see what you're showing.
For example, from the wall, you cut the metal or whatever.
Okay, so rolling the system that you get by rolling a graphene sheet is called a nanotube, and it has a very different structure than an actual wire. So the wires you can see as being cut because they are full. But in real life, these aren't cut nor rolled. The way to, I mean, you can, but it's very difficult. The way to make those hollow nanotubes is actually to start with carbon and start with a catalyst like nickel and grow them from scratch. So you don't really take a graphene and roll it. What you really do in real life is grow it from scratch, because you cannot have that kind of a control for rolling. Okay? Similarly, with wires, you don't really cut them, you grow them from scratch, usually. There are several ways of doing it, but usually it is grown from scratch. Okay?
That's maybe a funny, simple question, but since electrons are two small particles, the second and third dimensions, when they are really little, I think electrons should act in third dimension, still in third dimension. Why the graphics change?
It does.
It is really little, but it's still in third dimension.
Sure. This is why it is not, the density of states is not three-dimensional. But it's not two-dimensional either. So if it were really completely free in 3 dimensions, the density of states would look like this. If it were two-dimensional, completely two-dimensional, which cannot be achieved, it would look like this.
But in the last example, it's still three-dimensional. Nothing changed, just it's really small, but it's still in 3 dimensions.
Sure, nothing is strictly two-dimensional, nothing is strictly zero-dimensional, it's always three-dimensional. However, if you confine it enough, what does enough mean? Enough means that the distance between consecutive energy levels is below some threshold. You call it quasi-two-dimensional. Because it doesn't really act like a three-dimensional system. Okay? Of course, the boundaries of what is three-dimensional, what is quasi-two-dimensional, and what is two-dimensional is all blurred. I mean, there is no set point after which your system becomes two-dimensional. You can't do that. But as a rule of thumb, what you do is, if the behavior is sufficiently different from three-dimensional system, then it's quasi-two-dimensional. It's never going to be exactly two-dimensional, so it's quasi-two-dimensional. Everything is three-dimensional, of course.
I couldn't understand how this spikes stands for one-dimensionality.
Not the spikes. So if you, for example, look at this peak, and if you follow it until you hit the next peak, this peak is 1 over square root of E. And that is the signature of one-dimensionality. Okay? But it's not quite one-dimensional because there are several peaks. Good. Good questions. Keep them coming. Any more questions?
About the peaks on one dimension and those, the spikes doesn't came to be a shape, or does it?
Okay, so these, the tops you mean, they don't follow any particular trend? Is that what you're saying?
Yes, they doesn't follow a function.
Okay, so these should be infinite. Infinite spikes. But since this is a numerically rendered graph, this is a numerical effect. Because this isn't you cannot draw a continuous graph on a computer. So what you do is you have a set of really close points, and then you graph them. So the infinite part of it, where it blows up, always escapes. Because I don't have enough resolution to resolve the infinite peak in my computer. Okay? I drew it using a script, right, on the computer. So this is a numerical resolution problem. Really, these spikes should be infinite. Good idea. Other questions? So the next bit also has a lot of math, but I think it is late enough that we don't go into in quite so much detail. All I want to say here is that in real life, of course, materials are not that simple. So which materials, let me ask you. So all of the simple single electron stuff that I derived here, so this is really quantum mechanics, quite basic quantum mechanics. All of this stuff is for a bunch of independent electrons that are free or confined in, to 2-dimension or 1-dimension or whatever. But this is still a decent model for a particular class of materials. Can anyone think of this kind of material? So for graphene, for example, this is a terrible example. It really doesn't match the physics of graphene. But for some materials, it's okay. For a class of materials, it's okay. Can anyone think of this class? Semi-metals? What's a semi-metal? Graphene is a semi-metal. You are close. Metals. So if you are talking about metals, then metals really do behave like electrons in metals, for the most part, really do behave like free electrons. At least it's a decent approximation. But if you are looking at anything other than a metal, this physics is going to really break down. For example, oops, too much. Okay, this is too much detail. I won't go into all of that stuff. But if you take a graphene, material graphene, its quantum physics is very different from just a confined electron. Why? Because in graphene, no electron is really free. It is a semi-metal, like your friend said, so it has also high conductivity, but the conductivity happens through very different mechanisms than a metal. Because graphene is just a bunch of carbon atoms, so each carbon atom makes 3 really strong, incredibly strong covalent bonds. So much so that if you had a graphene that was like as big as a bed sheet, so if you took a graphene and blew it up and make it as big as a bed sheet, it would be able to lift up a full car. So graphene is incredibly strong, so these bonds are really strong. They are covalent, and the electrons are really localized on these bonds here. So it doesn't work like a free electron that is confined in one dimension. In order to describe the physics of such materials, we have, I don't have it here, but we have the full discipline of solid-state physics. So this is why my training as a solid-state physicist translates really well into nanotechnology, because it is the same idea. So in this case, when we have materials that do not act like metals, you have to look at their periodic structure. So you have these materials that really repeat themselves, and the physics gets modified because these particles, these systems, the wave functions of these systems repeat themselves. They are not confined necessarily to a wall, or maybe they are, but the idea is that they repeat themselves. There's a repetition that is very particular to each material. So all of this stuff, okay, is here, which I'm not going to go into because I can see that you were a bit tired, and also I am a bit tired, so maybe let's start to wrap up slowly. So what happens is that the energy structure of materials like this, not metals, but materials that are bonded covalently, okay, is a completely different kind of physics. So the way to describe the energy levels, so this is graphene, these are the energy levels as a function of wave vectors. So remember, we had the sort of concentric parabola. Now in graphene, because it's not like a metal and the electrons are not really free in that sense, it has a completely different energy structure. This is called a band structure, but it's really the energy function as a function of the wave number. As you can see, it is completely different. Right? If you look at the energy levels of nanotubes, so you take your graphene and you can roll it. Do I have a piece of paper? No. So let's say I have this piece of paper. You can roll it like this. You can roll it like this, or you can roll it sort of diagonal at any angle, right? And depending on the angle, the energy levels are so sensitive. It is so tiny. And the energy levels are so sensitive that depending on how you roll it, you get completely different kinds of nanotubes. If you roll them one way, you get conductors. If you roll them another way, you get insulators. So if you roll them with this angle, you get an insulator. If you rotate the angle and roll it like that, you get a conductor. Why? Because the energy levels, once again, these are the energy levels. So sometimes you get this point in the middle. When you get this point, it's a metal. When you get this gap, these are the energy levels as a function of wave number again. when you get this gap in the energy structure, it becomes an insulator or a semiconductor. So just by changing how you roll your nanotube, you can get different kinds of nanotubes. Alright, so I think I will stop you. Let's look at what we learned. So even if you don't remember a thing from this lecture, let's remember these things. So first of all, you cannot escape quantum mechanics. At this level, if you want to work in nanotechnology, you need to have a solid foundation in quantum mechanics. I would also say solid state theory, so that would be nice. Then, as you change the size of your system, or as you change the shape of your system, for instance, how you roll your nanotubes, or if you move the atoms around, your systems are so tiny that their energy levels change. They are very sensitive to these changes. By manipulating, by controlling these changes, you can change the properties of your materials. One signature is the density of states. The density of states, the signature of confined materials, is that their density of states is neither three-dimensional, nor two-dimensional, nor one-dimensional. So when you see that kind of signature density of states, you know that you are dealing with what we would call a nanoparticle. Okay. Same thing applies also to non-metallic structures, but the quantum mechanics becomes different. Quantum mechanics of periodic structures are different from other structures. So just by changing the periodicity, you can manipulate the energy levels. Like graphene and like nanotubes, the way you roll them, it changes the band structure and therefore it changes the properties. So, as a summary, we can say that confinement, making things smaller and changing their shape, really changes the physical properties, and it reveals a really rich physics behind these materials. All right, I think I will stop here. Are there any questions?
When you confine a material, how do you keep it in the volume? Will it not go back to its original size?
No, confined means you cut it. So nanofabrication is its own field. So physically actually making these things takes a lot of work. There are two approaches. One is called top-down. So you take a big chunk and then you cut. For instance, you take a laser and you cut, okay, to reveal small materials. Or bottom-up, which means that you fabricate them from scratch. So you make them to be in that shape, and then it keeps its shape. Of course, since they are really tiny, they are very susceptible to oxidation, temperature, heat, stuff like that. So you have to keep them isolated, somewhat isolated. You usually work in clean rooms, high vacuum, stuff like that. But once you make them, for the most part, they stay, unless your experiment destroys them somehow.
What's the future of solid state research?
For me, it is problems like catalysis, composites, polymer nanosystem, polymer composites with nanoscale particles, magnetism, health, the health sector, so medicine. So for me, since I'm on the applied forefront, these are the things I'm interested in. If you, or solar cell applications, if you talk to a pure solid-state physicist, which I am not, then they would have a different answer, and I don't really know the answer to that. But for me, it is these applications that are the future. In all honesty, the manufacturing of these materials is so expensive and difficult that they are unlikely to replace our current technologies in the coming several decades. So when I was a student, not like you, but older, when I was a PhD student, it was all this big deal of graphene is going to replace silicon electronics and stuff. 20 years later, no, it hasn't. Because there's the infrastructure already in place for the other stuff. It is very difficult and costly to switch to this kind of fabrication techniques. But slowly, they are finding applications, especially in medicine, mechanics, aerospace, solar energy, stuff like that. So slow, but this is the future from an applied perspective. From a theoretical perspective, talk to Ahmet Hoca. Other questions?
Hocam, there was a TED talk of yours a few years ago.
Yeah.
At there you mentioned an article of Richard Feynman about the basic idea of nanotechnology.
Yeah.
Now, after it's like nanotechnology is 20 years of field, but back then, what was his idea of how did he define the nanotechnology in his way?
So he said I don't know what inspired him to do that, because it is really ahead of his time. I mean, of course he was a genius. Of course this was, again, something expected, but he also had a lot of imagination. So he said that, why is it that? So you can make things really, really small, like you can make tiny little sculptures, for example, by just using really precise tools. But at some point, when you go to atomic level, you cannot even see that particle anymore. So he said that, can I imprint, for example, if I take a number of atoms and make a letter out of them, he said that I can write. Back then, of course, encyclopedias were a thing. I don't even know if you remember what they are. So we had these big books, encyclopedias, that had like 20 volumes. In every home there was like a set of encyclopedia. And at the time he concentrated on Encyclopedia Britannica, which was like 25 volumes, really thick volumes. And he calculated that if I decrease the size of every letter down to this many microns, I can write down the entire, I can translate the entire encyclopedia into the head of a pin. So he didn't really think about nanotechnology, because nanotechnology is a buzzword. Nanotechnology just is something that we invented to get money, basically, for our research. Seriously, I'm not joking. He didn't think of it in those terms. He just thought of it in terms of shrinking the size. I don't think, and of course the way he described shrinking the size was impractical, in fact. He didn't describe it correctly, but he envisioned making things really, really small. And he said that since it was the forefront of quantum mechanics, people didn't know all of this stuff in this way back then, of course. So he didn't really chart out a map, but he just envisioned making things really, really small. And that was enough.
So he was basically talking about confining information into a really small space.
Exactly. Later, this was done by just using atoms. There's a fantastic picture that spells the word, the acronym IBM, using xenon atoms. So you can count each atom, okay? And later, really recently, this was done by just holographic interference of light. So now the amount of information we can confine to a small space is insane. I mean, way beyond what Feynman imagined, right? But it's not just about confining information, it's also about making use of materials' properties. I'm not sure if he thought of this side of it. His idea was just confining information, compactifying information. Right, maybe we should stop. So if you want to talk afterwards, we can still chat, but I think this is a good time to stop. All right, thank you guys.